last tutorial of this first day of the workshop. And it's a pleasure for me to introduce Chris Jarzynski. And he will talk about the thermodynamics of strong coupling, systems with strong coupling. So Chris, please.
Okay, thank you very much. I'm very happy to give this talk, and thanks to all the audience members that that are sticking around for the last of the tutorials. So the title, as one just said, is Thermodynamics of Systems with Strong Coupling, and the strong coupling refers to strong coupling between the system of interest and its surrounding thermal environment. And when I was preparing these slides, I kind of realized that this topic is, in some sense, one that's inherently fairly detailed. So that's a kind of warning that you will see slides later on that have a lot of equations on them, and it's also kind of apology for that, especially to those people who may be listening to this talk at some ungodly hour in the middle of the night. But after all, this is supposed to be a tutorial, so I think it's fair game for me to ask you to get your hands dirty with a little bit of the technical details. So with that in mind, I've structured the talk as follows. I'm going to start by giving kind of a higher level overview of what this field or subfield is all about. Then I'm going to zoom in on one of the particular ways to approach it, and there I'll work through a lot of the details in detail, and then I'll zoom out toward the end again and look at different ways of approaching this problem. Okay, so let's start with kind of my favorite analogy between a macroscopic system and a microscopic system. On the macroscopic case, imagine I have some rubber band whose length is L. It's immersed in some surrounding air. And if I were to write down the total energy of this universe, and when I say universe here, I'm always meaning the system and its surrounding environment. The total energy of the universe, I would write that down as an energy associated with the system of interest, the rubber band, and an energy associated with the environment, which is the surrounding air. And of course, in writing down this equation, I'm neglecting the interaction energy between the system and its environment. That interaction energy is definitely there, but I'm pretty safe in neglecting it because the interaction energy, its magnitude, is actually really, really small compared to either of these other terms. So I'm not going to go very wrong by neglecting that interaction energy. And what I gain by neglecting the interaction energy is the notion that when one of these systems loses energy, then the other one gains the corresponding amount of energy. And this very naturally leads to the notion of heat in thermodynamics. So if the environment is losing a certain amount of energy, then that amount of energy represents heat that's flowing into the system, or vice versa. And once we have this intuitive notion of heat, we can combine that with the notion of work that we're already familiar with from mechanics, and that leads directly to the first law of thermodynamics. Heat, however, can also be used to define entropy. This is what Clausius did back in the 1800s. And once we have entropy, we have the second law of thermodynamics. So basically, starting from this heat, we end up with both the first and second laws of thermodynamics in the way that we all learned them, many, many years ago. But I'm emphasizing here that to get to these notions, we had to have this idea that when one system loses energy, the other system is gaining the same amount of energy. Now let me look at the microscopic analog. So imagine I have, let's say, a piece of RNA or some other polymer-like molecule. I attach the two ends of the molecule to some polystyrene beads, and then I take this entire system, I immerse it in water. So here my RNA strand attached to the beads is my system of interest. The water is the surrounding thermal environment. And then I can use a micropipette along with an optical trap or laser tweezers to trap this molecule. And by manipulating the distance between the micropipette and the laser trap, I can stretch the RNA strand or contract it very much analogously to what I can do with a rubber band at the macroscopic scale. Okay, if I now write down the internal energy of this little universe, then that's going to be composed of a term for the system of interest, U-sys. So think of this as the Hamiltonian for that describes the bare internal energy of all the atoms that make up the RNA molecule and the two beads to which it's attached. Similarly, there's an internal energy for the environment, the surrounding water, and there's an interaction energy between the two. And now in this case, I can't neglect the interaction energy, or more precisely, if I did, I'd be leading myself into grave error, because in general, this interaction energy is going to be comparable to the bare energy of the system of interest. Okay, so unlike the case that we had with the rubber band, this interaction term cannot be neglected because it's typically similar in magnitude to the internal energy of the system itself. Okay, and now we see that this complicates how to define heat, because if how do we define heat now when there's a certain amount of energy that resides in this interaction term, and that amount of energy in the interaction term can also change over the course of a process. So should we think of this interaction energy as belonging to the system or to the environment, or maybe somehow split the difference 50-50 between them? At some level, this may seem like basically a problem of accounting rather than a problem of physics, but we need to get that right if we're to have microscopically precise definitions of quantities such as heat and work and so forth. Okay, so with that in mind, okay, so at this point, if we want to write down, let's say, a first law and a second law of thermodynamics, we might take the following approach. We might say, well, in the macroscopic case, we had this very nice first law and second law because we were able to ignore the interaction energy. In the microscopic case, when the interaction energy is no longer negligible, maybe we'll need to write down some correction terms to the first and second law. So the first and second law may need to be modified with correction terms that account for this interaction energy. So that's one potential approach to this. But in fact, in this field, the approach that has been taken by most of the people working on it is instead to try to come up with microscopic definitions of all the quantities that we want, heat, work, entropy, and so forth. Try to come up with microscopic definitions that preserve the structure of the thermodynamic laws. In other words, we'd like to be able to introduce some definitions so that the first law and the second law still take exactly the same form that they did in a macroscopic case without needing to add any kind of ugly correction terms, so to speak. So that's kind of a broad goal of this field, and I'll specify it a little bit more in soon. But before going on, let me mention that these two equations introduce a kind of notational convention that I will use throughout the talk. Namely, when discussing any quantity that macroscopically would be thought of as an extensive quantity, like internal energy or entropy, if that quantity, if the value of that quantity is going to be macroscopic, then I'll use a capital Roman letter to indicate it. So here, for instance, the internal energy of the rubber band is denoted by a capital U because the rubber band is a macroscopic system. Similarly, the internal energy of the environment in this case is also denoted by capital U because because I'm assuming there's a macroscopic bath of water in which this particle is immersed. On the other hand, the internal energy of the system of interest itself and the interaction energy, those are really microscopic quantities, so they're going to be denoted by lowercase letters, and I'll use that notational convention throughout the talk. Okay, so let me now spend a couple minutes just reviewing some macroscopic thermodynamics. So how would we describe what's going on with the rubber band? Well, we've got air that's at some temperature T. The rubber band has a length L. We know that in macroscopic thermodynamics, everything is organized around this concept of equilibrium states. So I might think that, well, for my rubber band, if I specify its length and its temperature, then that uniquely specifies its equilibrium state. This then brings us to the notion of state functions. State functions are just quantities that have well-defined values in equilibrium states. So for the rubber band, we can imagine that it has some internal energy, U, that depends on the state variables L and T. It has some entropy S and some tension that I'll call psi. And we also know that it's useful in macroscopic thermodynamics to introduce thermodynamic potentials like the Helmholtz free energy, F is equal to U minus ST. So in this case, the first law seems fairly simple. The net change in the internal energy of the system when it goes from one equilibrium state to another should be equal to the sum of the heat that is absorbed by the system plus the work that's performed on the system. Either of these quantities can be either positive or negative, And by work here, I mean the mechanical work associated with stretching the rubber band. So it's the integral of the tension times displacement. The second law is written in the form of the Clausius inequality. Q is less than or equal to T times delta S. But in this isothermal situation that we have over here, where we only have a single thermal reservoir at one temperature, one can combine this inequality with the first law and with the definition of the Helmholtz free energy. And after some very simple manipulations, this can be rewritten as W is greater than or equal to delta F. So the work is greater than or equal to the net change in the free energy. And this is the form of the second law that one often sees for isothermal processes. Okay, everything seems kind of simple enough, but actually I haven't been entirely correct. I haven't been entirely honest here. Because the surrounding air, after all, doesn't just have a temperature, it also has a pressure. So in principle, I should use not just L and T, but LT and P as variables that specify the equilibrium state of my rubber band. Also, although we don't usually focus on this fact, a rubber band occupies some finite volume of space. Let me call that V. And in particular, if I'm stretching or contracting the rubber band, there's no guarantee that the volume of space that it occupies isn't going to change. In other words, when I stretch it, the volume might change by a small amount, but it might change either in the direction of increased volume or in the direction of decreased volume. And if that happens, then the rubber band is either doing work on the surrounding air, or the surrounding air is doing work on the rubber band. So if I want to be really precise about things, I really should write down the first law in the form shown over here. Delta U is equal to Q plus W, where W is, again, this non-PDV work. This is the work, mechanical work of stretching a rubber band, minus P times delta V. And this accounts for any work that is done on the rubber band by the surrounding air or vice versa. Okay, normally we neglect this term because it indeed is going to be a very, very small term, but it's not a microscopic term. This is a macroscopic, though very, very small term. So if we want to get the macroscopic thermodynamics really right, we should include it. So once we start talking about pressure and volume, we know that it's natural to introduce the enthalpy as a useful thermodynamic potential. H is equal to U plus PV, and the Gibbs free energy, G is equal to H minus ST. And then I can rewrite this first law by taking the TdV term to the other side of the equation, and I have delta H is equal to Q plus W, which is the natural way of expressing the first law of thermodynamics when dealing with processes that occur at constant pressure. And then the second law gets rewritten much the way it was in the previous transparency, but now there's this P delta V term floating around. So for the second law, we have W is greater than or equal to delta G, the net change in the Gibbs free energy. So really, I've been discussing two different ways of writing down the first and second laws. One of them is correct, which is this one, in terms of Gibbs free energy. The other one is incorrect, but still, it's a very good approximation that we can usually, generally get away with it when talking about rubber band thermodynamics. The reason why I'm bringing up these two different ways of doing it is because we'll see that at the nanoscale, when trying to describe nanoscale thermodynamics, we're also going to have multiple ways of describing the same process. So I'll get back to that point later. All right, so now let's go down to the nanoscale, and here I'm going to be describing the system using the tools not of thermodynamics but of statistical mechanics. So let little x denote a microstate of the system of interest. So again, the system of interest is this molecule here, and the surrounding and the beads to which it's attached. And by microstate, I just mean the positions and momenta of all of the atoms that compose this system of interest. So this is a vector in a very large dimensional space. I'll let little y denote the microstate of the surrounding environment. This is a vector in an even much larger space because it includes the positions and momenta of all the atoms making up all of the surrounding water molecules. And then finally, I'll introduce this work parameter lambda, which is the distance from the micropipette to the center of the trap. And that's a parameter that the experimentalists can control externally. We know that in nanoscale statistical mechanics, there are a number of fluctuation theorems that apply. So in particular, in this situation, Let's imagine that we have a process where we begin in one equilibrium state. Let me call it A. We then, let's say we stretch the molecule by changing the parameter lambda from A to B, and we end up in a different equilibrium state, lambda equals B. And imagine that I go and do this experiment over and over again, always stretching from the same initial equilibrium state A to the same final equilibrium state B. Because we're dealing with a very, very small system, thermal fluctuations are going to be non-negligible. So the precise amount of work done every time this is carried out is going to differ from one realization to the next. So at the end of the day, after many realizations, we will have the situation that's shown schematically over here. There's some distribution of work values, rho of W, and we would expect that the mean of this distribution should be greater than the free energy difference between the initial and final equilibrium states, but now fluctuations are going to be sizable around the mean, which is not something that we would typically see in a macroscopic system. And these fluctuations obey these so-called fluctuation theorems. So there's this prediction, which is an example of an integral fluctuation theorem. It says that the average of e to the minus beta w, where average is this average over this distribution of work values, is equal to e to the minus beta delta f. And then there's a detailed fluctuation theorem derived by Gavin Crooks, and this is expressed in terms of two different work distributions. So imagine that we have a forward process, what I'll call a forward process, where let's say we're stretching the molecule from state A to state B, and then a reverse process where we're contracting the molecule from state B back to state A. And again, there's going to be a distribution of work values associated with the forward process, a distribution associated with the reverse process. And what Crooks showed is that these distributions satisfy this very nice symmetry relation, namely the ratio of those two distributions is equal to e to the beta w minus delta f. I'm not going into much of the details of these fluctuation theorems because this isn't a talk about fluctuation theorems, but these will play a role in what I'll be discussing. So we have these two integral and detailed fluctuation theorems, and by the way, I should have mentioned either one of these immediately implies that the average work is greater than or equal to the free energy difference delta f. So we get the second law for free from either of these fluctuation theorems. But now, if you go back and you read the literature on fluctuation theorems, you'll see that in some of the papers, delta f appears on the right side of the equation. And I would say that's probably in the majority of the papers, but in a substantial fraction of the papers, it's delta g rather than delta f. Roughly speaking, the papers that are more on the physicsy side tend to have delta f, whereas the papers that involve, let's say, stretching of single molecules or discussions of such processes almost always have delta g on the right side of the equation. And what's worse, nobody seems to be bothered by this, that sometimes we use delta f, sometimes delta g. It's almost like the community can't decide which is which. And we should expect from macroscopic thermodynamics that there genuinely is a difference between delta f and delta g. So one kind of additional motivation for trying to come up with very precise definitions of all these quantities is to resolve, are we talking about delta f here, or are we talking about delta g? And of course, I'll get back to this point. Okay, so with all that as a kind of background, let me now state kind of the goal or a goal of this field, which is to develop a statistical mechanical framework, and by that I mean a framework that starts off with the positions of all the atoms and so forth. This framework should have the following properties. It should correctly describe the equilibrium state of the system of interest. I mean, if you can't do that, you'd better pack up and go home because you're not going to get anything else right. It should provide very precise microscopic definitions of all the relevant state functions that we may be interested in, such as internal energy, entropy, free energy, and so forth. And I should have added here that it also should provide precise microscopic definitions of heat and work. The framework should include explicit statements of both the first and second laws of thermodynamics, as well as fluctuation theorems. And hopefully we could devise frameworks that give these laws without any kind of correction terms accounting for strong coupling between the system and the environment. And finally, there's a fourth condition here, that we would like this framework to scale up to macroscopic thermodynamics when the system is large. And what I mean by this is the following, that a large system like a rubber band is also ultimately made up of atoms. So if we take the definitions that we've devised in this, in whatever framework we develop, and we apply them to a macroscopic system like a rubber band, then it would be nice for the values that come out of that to agree with the actual macroscopic values of internal energy or entropy or free energy or whatever we're talking about. I've put this condition in square brackets because it's logically, it's not really necessary. In other words, if we want to develop a framework and we're only ever going to use that framework to talk about microscopic systems, then maybe we're not going to be so interested in whether it scales up properly. On the other hand, if we want the framework that really interpolates from the nanoscale all the way up to the macroscopic scale, then this condition is going to be an important one. So two of the early papers that tried to develop such a framework, or at least early within this kind of recent activity in this field. One of them was by Udo Seifert in 2016, and then about a year later, I had a paper that took a different approach to this problem. So what I want to do now is kind of dive into some of the details of the approach that I took, and then I'll discuss why that is not the only way to do things, and that will lead me to a discussion of the approach that was taken in Seifert's paper. Okay, so let me go back to this picture I had over here. My system of interest, my surrounding environment, X, Y, and lambda have been defined. Now let me write down the energy of this little universe as a, okay, so I see that there's a, all right, so the total energy of this combined system, I'm going to write that as a bare energy for the system of interest. So think of this as including all the interactions among the atoms that make up my system of interest. And this will also depend on this parameter lambda. So I'm imagining that let's say that the optical tweezers here are forming some kind of harmonic potential that acts on the center of mass of this bead. Then I'm going to have a contribution from the bare energy of the surrounding environment. So this is just the energy associated with the water molecules and how they interact with one another. And then there's going to be an interaction energy that couples the two subsystems, the X for the system of interest and Y for the environment. Now, obviously, this is not the most general Hamiltonian one could write down. One could make either or both of these terms depend on lambda, but this is motivated by these kind of the physical situation that usually occurs in laboratory experiments. Okay, so this entire system and environment here is itself a macroscopic system, so I know that I'm fairly safe in using ordinary macroscopic statistical mechanics to describe the equilibrium state of this universe. So let me use the familiar Boltzmann distribution to write down a formula for the equilibrium distribution of the system and the environment. And now, starting from really these two equations, this is my starting point, I want to define all of the state functions that I'm interested in. In particular, I want to define a state function little u, which will be how I define the equilibrium internal energy of my system of interest, S for the entropy, V for volume, H for enthalpy, and G for Gibbs free energy. I'll talk about Helmholtz free energy a little bit later on. So again, these are meant to be quantities associated with the thermodynamic state of the system of interest, not the system and its surroundings. So these should be microscopic in magnitude. Let me also direct your attention to another notational convention. So notice that this u cis here, this is a lowercase u with a subscript cis for system of interest. That subscript appears over here, but it doesn't appear over here. So throughout this analysis, when I have quantities with the lowercase cis on them, those are going to be so-called fluctuating observables. And what I mean by fluctuating observable is some quantity that depends on the actual microscopic state of the system. So if you want, if you want me to tell you what U sub cis is, you should tell me where all of the atoms are located and how fast they're moving, and then I can tell you the internal energy of the system for that particular microstate. On the other hand, for these quantities over here that don't have that subscript, these are meant to be state functions. So these are functions of the equilibrium state itself rather than a particular microscopic state. So this U here without a subscript, this is the internal energy that's associated with this system when it's in a particular equilibrium state, and that equilibrium state is going to be defined by the values of lambda, the temperature, and the pressure, without having to give all of the microscopic positions and momentum of the atoms. So again, the subscript cis denotes a fluctuating observable. No subscript denotes a state function. Okay, so now let's get into some of the analysis. Again, I'm starting from the familiar Boltzmann distribution in the full phase space. Here's my total Hamiltonian. And if I want the equilibrium distribution for the system of interest, all I need to do is integrate out the y variables, the degrees of freedom of the environment. And I can do that in a few lines, and that gets me to this equation over here, namely that the equilibrium probability for finding the system in a microstate X is going to be proportional to this kind of modified Boltzmann factor, where this phi term is a modification that accounts for the strong coupling between the system and the environment. In fact, I should expect that this phi should vanish when the coupling between the system and environment is very, very weak, because then I would normally expect the usual Boltzmann factor. And if you go through this exercise, you'll find, and again, it's just a few lines long, you'll find that the explicit expression for this phi is given by this equation that appears over here. Notice that the phi depends on x. It does not depend on the parameter lambda. So it's given by the expression that you see over here. And indeed, in the limit when this interaction energy becomes negligible, we have the numerator and the denominator become identical, and then phi vanishes as expected. Now, not only do we have an explicit formula for this phi, but there's a very nice physical interpretation of it. Namely, phi of x is the solvation free energy for the system in the frozen microstate X. And what I mean by that is if I were to take my molecule and to freeze it in a particular configuration X, so the atoms are frozen, so to speak, and if I were to take that molecule and then reversibly insert it into the water, so I'm starting with a molecule outside in vacuum, and then I reversibly insert it into water, there is a free energy associated with that change. That free energy is just the reversible work that I need to do to place that molecule in water. And that work mostly is associated with pushing the water molecules out of the way so that there's a cavity large enough to accommodate my molecule. So it turns out that this phi of x is exactly equal to that reversible work to insert the system in the environment if I imagine the system is frozen in this configuration X. Okay, so we've kind of accomplished the first thing, which is writing down an explicit formula for the equilibrium distribution. But I shouldn't take any credit for this. This was done already almost 100 years ago by Kirkwood, and all of this is very familiar to people who work, let's say, in solvation chemistry. But this will be useful for very useful for the following analysis. Okay, let me now try to get a little bit of intuition for this solvation free energy, and I'll get that intuition by seeing how it works out for a macroscopic system. So suppose instead of taking a single molecule, I'm going to take a small pebble and insert a pebble into water. Phi is, again, it's the solvation free energy. It's the reversible work that I need to insert the pebble into the water. And I know what that is from macroscopic thermodynamics. That's just the pressure of the water times the volume of the pebble. This is the cost, the thermodynamic cost of creating a cavity in the water that's of exactly the right size to accommodate the pebble. But now I can take this equation and flip it around and say, the volume of the pebble is therefore equal to this solvation free energy divided by the pressure of the surrounding water. And this gives me a way to kind of define the volume in a thermodynamic fashion. So this is a thermodynamic definition of the volume of the pebble that's different from the usual geometric definition, which involves the measure of space that's enclosed by the surface of the pebble. The values are the same. So the value of this thermodynamic definition is the same as the value given by the usual geometric definition, but they're defined in two different ways. Now, this may seem like just kind of a way of complicating things, except that when we now go back down to a single molecule, the definition of the volume of a single molecule is not really, it's the volume of a single, geometric volume of a single molecule is not unambiguously defined because we don't have a sharp surface to a single molecule. On the other hand, the solvation energy for a single molecule is very well defined. I had the equation for it on the previous transparency. So for a microscopic system in water, it makes sense to actually define the volume thermodynamically rather than geometrically. So let me just put forward this definition. The volume of my molecule, when it's in a particular configuration or microstate X, is just going to be the solvation free energy associated with that microstate X divided by the pressure of the surrounding water. And because this volume depends on the microstate, I'm going to have this subscript SYS here. This is another, it's a fluctuating quantity. In equilibrium, as X fluctuates, so does the volume of the system. Okay, let me now take that definition and combine it with the expression that I had for the equilibrium distribution of the molecule. So here's the expression that we already had before. I'm defining the volume in this way. When I combine these two, I see that I can rewrite this Boltzmann factor as e to the minus beta ucis plus p times vcis. And this is nice because this is starting to look like the isothermal isobaric version of the Boltzmann factor, right? So this is the Boltzmann factor at constant temperature and constant pressure, looks something like this. I can then combine these terms, internal energy plus pressure times volume, into yet another fluctuating observable, the enthalpy, H of the system. So notice that at this point, I have three different fluctuating observables: the internal energy, the volume, and the enthalpy of the system. Now, from these, let me start introducing some definitions for state functions. So I'm going to define my state function U. So again, this is the internal energy associated with an equilibrium state rather than a particular microstate. I'll just define U to be the equilibrium average of this fluctuating observable. So it's the average of ucis when the system is in equilibrium. Similarly, I'll define the equilibrium volume to be the average of this fluctuating volume, and the equilibrium enthalpy is just the average of this fluctuating entropy. So I've got three of the state functions I want to define down. For entropy, I'm just going to use the usual Shannon formula, and I'll define the entropy of my system in this manner. And finally, for the Gibbs free energy, this looks like a Boltzmann factor. It is a kind of a Boltzmann factor. So I'll define the Gibbs free energy as minus kT times the log of the corresponding partition function. So it's minus kT times the log of the integral of this Boltzmann factor over the phase space of the system of interest. Okay, so far, again, I haven't really made any predictions. All I've been doing is introducing definitions. But you can show, and I'll leave this as an exercise, that with these definitions, the quantities that I've defined over here are related by these two equations. H is equal to U plus PV, and G is equal to H minus ST. There's no approximations over here. These equations come directly from the definitions that I've introduced. And of course, these equations are identical to the usual relationship we know between internal energy, enthalpy, entropy, and Gibbs free energy and volume for macroscopic systems. So at the very least, these definitions preserve this kind of structure from macroscopic thermodynamics. Okay, but again, I haven't made any physical predictions. So far, it's just definitions. In order to make physical predictions, let's now start looking at the first and second law. Okay, remember at the macroscopic scale, this is the expression for the first law of thermodynamics. Here are the various definitions I've introduced. And now let me imagine one realization of a process where the work parameter lambda is being changed externally from A to B. So let's say I'm stretching the molecule, and the system then evolves in its phase space along some trajectory x of t. Of course, really what's happening is the system and the surrounding environment is evolving in this much, much larger phase space, but I'm ignoring what's going on with the environment. So if I let delta USys denote the net change in this internal energy from the initial time to the final time, then identically, this is equal to the integral of its total time derivative. So this is the integral dt x dot du sys dx plus lambda dot du sys d lambda, where the dots here just denote time derivatives. And then I can rewrite this u sys here as h sys minus the product of pressure and v times sys. So that gets me to these two expressions over here. So I first have time integral of x dot dh sys dx. And then because the p here does not depend on lambda, I can rewrite this contribution as simply p times dv sys. And then I have this contribution over here, which just carries over. Okay, and now this is starting to look a little bit like the first law. So let me define the heat to be the time integral of x dot dh sys dx, and work to be the time integral of lambda dot du sys d lambda. So these are these two terms over here. But I can rewrite that second term as the integral of lambda dot times dh sys d lambda. Again, I can do that because this quantity doesn't depend on lambda. And now, having rewritten things, then I kind of get, by construction, I get the first law back, namely the change in the value of this fluctuating internal energy is just the heat absorbed by the system minus P times the net change in this fluctuating volume plus the work that's performed on that system. Okay, everything so far has been for one realization of the process. Now imagine that I repeat this process infinitely many times. So I have an ensemble of realizations, and I'm going from one equilibrium state to another equilibrium state. If I take the average of both sides of those equations, then I get the following result. So the average of this now just becomes a net change in the equilibrium internal energy between the equilibrium state at A and the equilibrium state at B. And that's equal to Q in angular brackets. This is just the average heat absorbed over many repetitions of the process, minus P times delta V. This is again now a change in the equilibrium volume plus the work. And I can move this term over to this side of the equation to get delta H is equal to average Q plus average W. So with these definitions, I've recovered the first law. That was kind of the easy one. What about the second law? And that's where we can see whether all of this hangs together or not. Well, it turns out, and this is a little bit more of involved calculations. I'm not going to do it here, but having defined work in the way that's shown over here, the way I had on previous transparency, that definition of work automatically leads to both the integral and the detailed versions of the fluctuation theorem for this process, as long as we use delta G on the right side of the equation. Okay, so these two follow as identities from this definition of work, along with the assumption that the system begins in a state of thermal equilibrium. Okay, once we have these, as I think I may have mentioned before, maybe not, from either of these equalities, one immediately gets the following inequality that the average work is greater than or equal to the free energy difference delta G. Okay, so at this point, I've shown that kind of starting with this definition of fluctuating volume, everything kind of falls into place from that definition, and we have definitions, all the state functions that we wanted to have defined, internal energy, entropy, and so forth. There's microscopically precise definitions of work and heat, and these various definitions satisfy both the first law, the second law, without any kind of correction terms, as well as these fluctuation theorems. So it seems that the task is done, and it also seems that we've answered the question, should this be a delta G or a delta F? The answer seems to be delta G. Okay, well, maybe not so fast, because it turns out that this is not the only way to do things. What I want to do now is go through several, and I'll do this much more quickly, three different approaches that I'll call alternative approach 1, 2, and 3 to the same problem. So let me start with the simplest one. And again, alternative approach 1 is just to ignore volume, never pretend as if the concept never existed. So again, let's start with the expression for the equilibrium state. That's in some sense always the starting point. Previously, I had rewritten this in this form by defining volume in the way that I did, but let me not do that this time. And instead, let me just take the stuff, the sum that's in parentheses here and call that something else. Let me call it U star cis. So this is just a definition. And now this looks like an ordinary Boltzmann factor, but with a kind of, I don't know, renormalized energy. So we can now say, let's treat this as a kind of system's internal energy. It's not just the bare internal energy, but it's somehow the internal energy plus some modifications due to coupling to the surrounding environment. But I'm just looking at this, it looks like a Boltzmann factor, so maybe it makes sense to think of this as an internal energy. This quantity is actually often called the Hamiltonian of mean force, for reasons that I'm not going to go into. But this is let's just think of it as a kind of effective free energy for the system. Okay, here are all of the state functions that I defined in the original approach that I've just spent several slides going through. In this alternative approach, first of all, I'm not going to worry about volume or enthalpy because I'm ignoring the volume. So in this alternative approach, let me just define the internal energy to be the equilibrium average of this Hamiltonian of mean force, of this effective energy. Again, this is just a definition. I'll call it U tilde. The tilde here is just simply to distinguish this definition from the previous one that I had used. So all the tildes are associated with this alternative approach. There's no reason for me to change the definition of entropy. So in this alternative approach, I'm still going to use the Shannon expression for entropy. And now, because I'm ignoring volume, and this looks like an ordinary Boltzmann factor, let me define the Helmholtz free energy associated with this equilibrium state to be minus kT times the log of the corresponding partition function. So minus kT times the log of the integral of this Boltzmann factor over phase space. Okay, so these are just three definitions that I've introduced that kind of seem reasonable by starting from this, if you start from this expression. And you can easily convince yourself that actually these three definitions are the same as H, S, and G that were introduced previously. I'm just calling them something else now. Well, S is obviously the same because nothing has changed, but the U tilde is just what I previously had called H, and F tilde is what I previously called G. Okay, so let me kind of wipe the board clean and put these equations up here. And now let me define work and heat in a way that should be familiar to people in stochastic thermodynamics. So the work in this particular approach, W tilde, is equal to lambda dot, the integral of lambda dot times this renormalized energy or effective energy, a derivative of U cis star with respect to lambda. And similarly, heat in this alternative approach is the integral of x dot du cis star dx. And it turns out that these two definitions are exactly the same as the definitions previously. Sorry, that's not right. The heat is different. This should be an inequality. The work, however, is exactly the same as before. All right. So then it turns out that from these definitions, you can show that all of these results still hold. And in fact, these are not new results. These are exactly the same results that I had a couple of transparencies ago, but now I've rewritten them in terms of the new names that I've assigned, to these quantities. And sorry, I have to take that back again. I just confused myself. This should be an equality. The Q tilde and Q are exactly the same, and you can confirm that by going back to the previous definitions. So again, all I've done here, there's no new math here at all. I've just basically introduced new definitions that seem reasonable if you start from this expression for the effective Boltzmann factor. And with these new definitions, if I just rewrite all the equalities I had before, an inequality in terms of these new definitions, then I get the results that appear over here. And this is kind of what you would expect from a thermodynamics description when in a situation where volume is not relevant, where volume and pressure are not particularly relevant. So the bottom line is that we already see that there's more than one way of describing exactly the same thermodynamics. So, what you call a Helmholtz free energy difference, I may call a Gibbs free energy difference, and we may both be right. This isn't like the macroscopic case where one of them is right and one of them is wrong. Both of these are equally valid kind of approaches or equally valid sets of definitions. All right, let me now move on to alternative approach 2, where we're not going to ignore the volume, but still we'll define quantities differently. And I'll call this the partial molar representation, and I'll explain why in a moment. So here, in addition to the equilibrium state that I'm interested in, which involves my system and environment, I'm going to have a reference equilibrium state which involves the same environment, but there's no system of interest here. So, I've taken the molecule out and thrown it away, and here's the environment sitting around in equilibrium. Okay, as before, here's my starting point, the expression for the equilibrium state of my system of interest after tracing out over the environment. Okay, and now let me define the fluctuating internal energy of the system as a function of its microstate x and the parameter lambda as the following difference. Let me explain what these two quantities are. So UE0 here is just the equilibrium and equilibrium internal energy of the environment without any system. So this is the equilibrium energy of this reference state. UEX over here is the equilibrium system of, the equilibrium energy of this system over here when the molecule or when my system of interest is frozen in the configuration of X. So imagine I take this molecule, I freeze it in configuration X, I insert it into the environment, and then I allow the environment to come to equilibrium while holding the molecule frozen. That's a macroscopic system that can be described by the usual, statistical mechanics, and the average equilibrium energy of that system is what I'll call UEX. So then I'm defining the internal energy of my system of interest as the difference between those two. So in effect, this tells me I'm taking I'm defining the internal energy of the system of interest by the effect that I have on the total energy upon adding this system of interest to the bare environment. Okay, and I'll define volume and enthalpy in exactly the same way. And here I'm using overbars again to distinguish between the previous definitions for these quantities. And the reason why this is called the partial molar representation, or why I call it that, is that in chemical thermodynamics, if you have some solution, then which has a mixture of various different molecular species, then let's say the partial molar volume associated with one of those chemical species is the increase in the volume of the total system that you get by adding one more mole of that particular species to the mixture. So there's a similar kind of similar spirit here that we're defining the internal energy of the system in terms of the effect on the total system and environment that you get when adding the system to the environment. Okay. Let me now define the state function. The internal energy associated with an equilibrium state is just the equilibrium average of this fluctuating internal energy, and similarly for volume and enthalpy. And let me define the entropy of the equilibrium state as the equilibrium entropy of this whole system minus the equilibrium entropy of the reference system. Okay, and similarly, let me define the Gibbs free energy as the Gibbs free energy of the total system and environment minus the Gibbs free energy of just the bare environment. So it turns out that this definition of entropy is not the same as the original one. So this entropy is not going to be equal to the Shannon expression applied to this probability distribution. It just isn't. On the other hand, you can show it follows from these definitions that this particular definition of Gibbs free energy is exactly the same as the Gibbs free energy that I defined earlier. So that hasn't changed. And if I now define work and heat in the usual way that we do in stochastic thermodynamics, so work is the integral of lambda dot dh d lambda, Q is the heat is the integral of x dot dh dx. Then these two definitions of work are the same. So the new definition of work in this alternative approach 2 is the same as the old definition of work, but the new definition of heat is not the same as the old definition of heat. And here, this is correct. It turns out that, and this is a little bit more of an involved calculation, it turns out that in this case as well, both the first and second laws and the detailed and integral fluctuation theorems remain valid in this representation without any kind of, without the need to introduce any kind of correction terms. And these results are not just exactly the old results rewritten in terms of newly defined quantities. These are new results that are obtained for those quantities. All right, so that's the alternative approach 2, and then finally alternative approach 3 is just what you get by adding 1 and 2 together. And this is essentially the approach that Udo Seifert did in his paper. So in this approach, first of all, you ignore the volume, so there's not going to be any talk about enthalpy or Gibbs free energy. Everything is in terms of internal energy and Helmholtz free energy, and you define quantities such as internal energy using this partial molar representation, where all quantities are defined in terms of the effect of adding the system of interest to the environment. And again, I'm not going to write down the equations, but the first and second laws, as well as the fluctuation theorems, remain completely valid in this representation. Okay, so this kind of brings me to the end of the more technical portion of my talk, and actually almost to the end of the tutorial. But to summarize, in macroscopic thermodynamics, we have these well-defined notions of equilibrium states, state functions associated with those equilibrium states, thermodynamic potentials that can be built out of those state functions, heat and work, and the first and second laws of thermodynamics. So for a process that occurs at constant temperature and pressure, here's the usual way that we would write down the first and second laws. And the question that's kind of at this heart of at the heart of this field of strong coupling thermodynamics is, to what extent can we replicate this structure for nanoscale systems, or can we replicate this structure for nanoscale systems without having to introduce correction terms that account for the fact that in the nanoscale context, the coupling between system and environment is strong? And the answer to this question, as I hope I've convinced you, is yes, but the solution is not unique. There are multiple ways of doing it. So you kind of choose your favorite favorite approach and then run with it. And as long as you're consistent within that approach, all the predictions that you make about outcomes of possible experiments should be valid. Okay, so I've covered kind of a small amount of territory of this in this field. This field has been has had a lot of interest in the last few years. Okay. Okay. So let me finally mention, just to give you references to a relatively small number of papers, and obviously I can't be comprehensive here, so I apologize to those people whose papers I haven't referenced here. But if you're looking for review articles or a tutorial, the two Peters, Peter Tochner and Peter Hange, wrote a colloquium in Reviews of Modern Physics a couple of years ago. This focused on the classical aspects, which have been the aspects that I focused on throughout this talk. I should say that this colloquium is actually fairly critical of a number of approaches taken in the field. For instance, I was criticized very much for using the Shannon entropy to define entropy in the approach that I took. And other people were also criticized for some of their choices. So it's a very interesting colloquium to read. There is a paper by Strasberg and Winter in PRX Quantum from about a year ago. The main focus of this paper is not strong coupling, but it's a nice kind of tutorial style paper that does include a discussion of strong coupling. So that may be interesting. And finally, very recently, there's a paper by Trushechkin and colleagues that does focus on strong coupling in the quantum case, and what are the kinds of things that people have been able to derive, particularly some things that they've been able to derive with mathematical rigor about the quantum case. And again, the quantum case is something that I've ignored entirely throughout this talk. Here are a handful of papers related to classical systems in the strong coupling limit. So in 2017, Strasberg and Esposito took a kind of coarse graining approach to this problem, which is somewhat different from the way I had approached it or from the way that Udo Seifert had approached it. Harry Miller and Janet Anders looked at entropy production and time asymmetry in the context of these kind of strongly coupled systems. And then Eric Orell had a very nice paper where he really focused on time reversal as a kind of a key ingredient in the discussion of these strongly coupled systems. Strasberg and Esposito in this paper in 2020 addressed the question of whether the mean force Hamiltonian is a measurable quantity. And I think this was in direct response to some of the criticisms in the paper by Tochner and Hange. And much more recently, and I haven't really absorbed this paper yet, much more recently, there's been a paper by Ding and Tu and Xing on timescale separation. So they show that a lot of the structure comes out very naturally if one assumes a separation of timescales. In everything that I presented, we don't need to assume that, but they show that if you do assume that separation of timescales, things follow in a very natural way. On the quantum side, Perronneau-Lobé and colleagues have discussed corrections, actually, what they feel should be corrections to the second law that arise from strong coupling. There's a very nice paper by Funo and Kwan who approached this using a path integral formulation of quantum mechanics. Du and colleagues used a density matrix expansion where they basically took the density matrix and expanded it in powers of the driving, the rate at which the system is being driven. Strasberg investigated this problem in the context of the repeated interaction framework. There was a paper by Rivas, which showed how much you could get by assuming that the initial state of the system and the environment is a product state in the quantum case. Shang and Hu looked at this from a quantum field theoretic perspective, and recently Kresser and Anders did a comparison of the weak coupling limit and what they call the ultra strong. So the strong coupling limit is what I've been describing. Ultra strong is a situation where the interaction term actually dominates over the internal energy of the system of interest, and you get some very nice results there. So again, this is just kind of, these are meant to be a starting point. It's not meant to be a comprehensive list of papers that are in this field. And with that, let me thank you for your attention. I guess there's still a little bit of time left for questions.